All right, the short overview. I'll give you a little information about our institute, backup goals and limitations, what we can do and what we cannot, the challenge we're facing with scientific data, our implementation of the backup system, the configuration strategy we have with Bareos, and then the title of the presentation, Virtual Full Backups. I chose that because virtual full backups are not very often seen in the wild, as far as I can tell. Then the integration with third-party tools, HA setup with DRBD, and integration with REAR, which we'll hear about later this day as well. And yes, we do have a wish list. Okay, the Max Planck Institute for Radio Astronomy was founded in 1966. I'm sorry. That's no problem. We have two sites, the main building in Bonn and the 100-meter dish radio. All right, where was I? We have a two-site setup. We have the main building in Bonn, and we have a 100-meter dish, which you see in the background, radio telescope in Effelsberg, which is 40 kilometers away. Another telescope we operate is the Apex telescope in the Atacama Desert in Chile at 5,000 meters above sea level. Most of our servers we operate use Debian Linux, and we have a few of Windows Server where we can't help it. 110 of those are Bareos clients. We are operating that with an IT staff of 11 people, and we have a small cluster within a scientific group. If you want more information, please check our website. Another telescope we operate in Effelsberg itself is the LOFR antenna field. It's a station. We are part of 44 stations all over Europe. It's a so-called software telescope. It takes all of the data. It has no moving parts. It monitors all of the sky and reduces the valuable things or the things you want to see just in software, which means get lots of data and take a little tiny piece out of it. That's one of our main sources of scientific data. Let's see what that is. Well, we have quite a few experiments we employ with those telescopes, and that adds up quickly, just scientific raw data. Sometimes within 1 week, we're just short of 200 terabytes. If we try to back those up with our current setup, we'll forget it. Can't do that. It just takes too much time. Another thing why we cannot back up that much data is that post-processing of the observation data is done right after the observation, because scientists are very, very eager to get hands on their just recorded data. So we do not have a single I/O for backup left there. If we do that, the people wouldn't be happy. Anyway, let's see what we can do. The goal of a standard traditional backup is the fast recovery of specific files or directories, which are usually user errors. They deleted something, you want to restore that. Or maybe many complete system within a disaster recovery. The limitations with that is mostly in time, because we have a small backup window. Scientists are nightbirds. They tend to work at night as well. Network bandwidth, which we usually have at 1 gigabit per second, rarely 10. And the most important resources on backup clients, I/O, RAM, CPU, it just takes time to process the data, check every file, and so on. Storage space, of course, disk and tape. If you have enough money, well, buy more. If you don't, you got to live with what you have. What we can do to counteract those limitations are parallel jobs. if you have enough bandwidth from many clients and put that onto a bigger line into the backup server, you can use parallel jobs. Virtual full backups is a quite valuable means to counteract, and volume retention, of course, we all know that. Okay, the remains of the day without the raw data. Currently, we back up 55 terabytes of a full backup, differentials, incrementals. What we like to have is, because we have that two-site setup, we'd like to have two copies, two backup copies, one in Effelsberg, one in Bonn. Okay, let's see how we do that. Let's pretend that our network speed we get into the backup server is the same speed we write onto an LTO5 drive, which we use. It's a little fast for the backup, but if you do parallel jobs and have a 10 gig line to your backup server, that's not out of the world. Let's see, we need to spool that, so we get that onto disk and write that to tape. So that's twice that one. And we want the second copy. So we multiply that by 2 as well. Count that in days, and well, 3 weeks of a full backup straight. Well, it's in your daily or weekly schedule, that doesn't really fit. So we came up with a strategy of so-called high-volume long-term clients. We talk to the clients, talk to the people, the scientific groups, and try to identify the large amount of data we need to back up. That usually tends to be more static as the rest of it, like file servers and all that. So we talked to them, and they were willing to go with a half-year full backup and incrementals on every Saturday. So it's a complete different story. You only have to do your full backup once every half year, which is better than doing it every 8 weeks. That leaves us with a full volume of 5 terabytes. We can do that. That's easy, because that takes 2 days. That fits into a weekend where you usually do the full backups. Okay, that's the backup hardware. That's a sort of a to show off what we have. Cool hardware. We use with 2 tape libraries, one in Effelsberg, one in Bonn. We use the 2 frame libraries, and that's marked in green. It has 2 LDO5 drives, lots of slots for tapes. We use 2 physical servers, one in Bonn, one in Effelsberg, of course, 2 RAID storages, and mostly dedicated 1 gigabit Ethernet for the backup network. And the backup server itself, as you see in that slide, is hooked up with a 10 gigabit line. So what I just mentioned was that usually all of the clients go into the backup network with a 1 gigabit, and the backup server pulls parallel jobs into its storage with a 10 gigabit line. The trick in that setup, I think, is the transparent ZAN. It's a fiber channel ZAN, and the backup server can transparently access both of the tape libraries and both of the RAID storages. It's just a device in the server, and it doesn't matter if it sits in Effelsberg or in Bonn, which makes the setup quite easy. Although there's a 40-kilometer distance in between. Yes, we do have dark fibers, which is very nice. There are still quite a few clients which connect with the standard LAN. They all use transport encryption using TLS, which Bareos supports. Tape backups, like full and differentials, go to Effelsberg first to get the first copy offsite. Then it's copied back to the Bonn library. The database, the Bareos database backup goes to Bonn and Effelsberg. It's very important. You don't want to lose that ever. Okay, basic configuration strategy in Bareos. We put the incrementals to disk for a better restore performance. It showed that if you put the fulls and differentials on the or if you put the incrementals onto tape as well, the restore takes lots more time. So we put that on disk. They tend to be smaller, and we only keep those for 14 days, and then recycle. We keep a very strict per client config with a director configuration and SD configuration, which makes very easy templating for tools such as Puppet we heard about. In addition to that, you can configure each client with different file sets, compression, quota, you name it. It proved very helpful not to have that little tiny change you want to make spread out on many, many clients. Once you did that, you can focus on schedules and retention. That's, I think, the most delicate part in a backup system. If you do anything wrong there, you get problems. We have a third-party tool to do our daily backup summary. Bareos usually sends you mails for every job it did. We have 110. That tends to get tedious to check all those. One could do things with email filtering, but it's just a nice thing to have to see, well, you have 2 failed jobs, 3 with warning, and the rest was okay. That's called Bacula reports still. I fixed that a little bit so it looks more like Bareos. It's basically hooks into the mail system, the mail command in Bareos, and holds that off as a spool and then sends it once a day, and has little shiny PHP stuff around it, and so it looks nice. It has links to the reports for every client and all that. But I think the web GUI will do that sort of job pretty soon too. I guess, I hope. Yep. Another thing we did is have an extra partition for the database. It's a nice to have, it's not a must. I think the speed hasn't risen that much. And other stuff, if you want to know about, please ask me. Okay, let's get to virtual full backups. They're not very often seen. How many people use virtual full backups here? All right, 1. Okay, probably complete different story, but well, it's anyway, same concept. All right, let's get to the concept. What it does, it takes the existing backups on tape, on disk, within the system, like folds, differentials, and the subsequent incrementals, and uses them to put that into a new full backup. It reorganizes them. The TSM version of that is called a reorganization as well. That's very nice because the client is not needed for that. It's all there. It's you have the full backup, your full pull. We took that 2 months ago. The last differential from 1 week ago, and all the incrementals, put that together. You got to have to put that into a new pool, because if you put that in the full pool, it could be that it wanted to read and write to the same device, and that's not possible. So you have to put that into a new pool, and then do for the next full backup. 8 weeks from now, you get to migrate that to your full pool. Takes quite a bit of time, but the client is not needed. No IOs, no RAM, no CPU usage. You have all time you have within that 8 weeks. Very nice thing to have. That's why I get those 3 pluses on the no backup client interaction. The backup window widens up significantly. The drawback I just mentioned is you need the designated pool to avoid the lockups. And up until now, we have no max full interval config option. We can talk about that later if you want to know what that is. Most of you probably do. It's a very easy way to figure out your full backup schedule with the retention that goes with it. So you never do mistakes there. All right, let's get to the third-party tools. DRBD is a widely used common setup for high high availability feature in Linux setups. What it does, it has 2 servers, 2 machines, and it's a block device mirror over network. It's a block device on the 2 servers, but you can read and write to it as if it were a local hard disk. Very nice. It has an active-passive setup, so you can only use it actively on one server and cannot read or write from it on the other, but it still gets mirrored. Standard HA feature in Linux setups. What you can do with that is you can do upgrades of a service, let's say an IMAP service, and you can upgrade the operating system, the IMAP service itself without downtime at all. You just do that on the secondary, on the offline server, do all your upgrades, move your service from the active one to the passive one now, and do the same thing on the other, and you're all set, and nobody noticed. Very nice. You can even do that with file servers. So that brings us to the point where, how do we back that up? It has a moving block device. We want to have the user data backed up, and the 2 machines. One could easily say, well, always back up the primary, but if your primary stays primary for, I don't know, half a year, you lose the data on the secondary, operating system, configuration, whatever you name it. So what we came up with was have 3 clients for such a setup. One for the servers themselves, the operating system setup, and one for the user data, and that's an additional Bareos instance, HA controlled. It just moves with the device. So we always have a consistent backup of all 3 databases, so to call. And that works very well, actually. Next one is REAR and the integration with Bareos on that. We're going to hear that later today. So I'm going to be fast on that. What it basically does is it's a Linux bare metal discovery solution. It creates, once it's installed, and once you call the tools for that, it creates a bootable media like ISO images, Pixie, USB, you name it. And if somebody takes a baseball bat to your server or burns it, you just use a new hardware, brand new, put it right there where it was, put in the CD or Pixie image, let it run for, I don't know how much data is on there, but runs for half an hour, and you're up and running again. We just had that 2 weeks ago in Effelsberg. I was sitting in Bonn, and the admin called me. We had a hard disk failure. The server doesn't work anymore. We cannot observe. Very bad thing. So I sent him the ISO image. He put that in, and I don't know, after 45 minutes, he was calling very happy. Oh, it's all working again. It's just what it says: relax and recover. It's not a hassle. You got to do. It takes care of all of the partitioning, RAID configuration, file system creation, and then the nicest thing about that is it can use the Bareos last full backup or the Bareos infrastructure to get the valuable data back onto the client without any user interaction. That's very cool. And that's all there is to the config. You tell it to output an ISO, in our case, use the Bareos backup system for restore, and you need to tell it where to put the ISO. That's it. In this case, rsync to our backup server, where it gets mirrored and all that, so it's all safe. And on the backup client, it's just another console you need to configure. It's not as easy as shown here, but basically you just need a console which can access the restore data of your client on the Bareos server. That's it. On the server itself, you need the counterpart of that. The ACLs are here to restrict the client to its own backup, so that some file server cannot access the other. It's so easy, why not do it? It's just a cinch. For the rest, check relaxandrecover.org. Actually very easy. All right. Last slide is our wish list. We just yesterday talked about the integration of virtualization solutions on hypervisor level. That that's a work in progress, which is very nice, and we very much support that, and will do so in the future. What I'd like to see is in Bareos to write to more than one destination, one storage device at once. That would obsolete time-consuming copy jobs. I told you that we have 2 copies of the data. Take it, I spool it, write it to tape, then get it back from tape, need to spool it again, and write it to another tape. Takes ages. So it'd be nice to have something, you get the spool file onto the disk and then write to 2 tape libraries at once, in our case, or any. That'd be really cool. Would cut down those copy jobs, the time-consuming copy jobs very much. Another thing to speed up writing to tape is a rolling spool-despool. That has been discussed in some news groups as well, mailing lists. If you start to spool data and get, I don't know, 50 gigabytes worth of that data on disk, why not start writing to tape while you get the data in? If it fails, you just have to redo it. But if it does work, then you cut the time you need to write to tape in half. That's, I think, would be a very nice feature to have. Another thing was we do the incrementals to disk, and for some reason I did my retention stuff all wrong. It gets upgraded to a full, and then it's got to write to tape. You can have that configuration that you write automatically to tape within that, but you cannot tell it to spool then. So you do some shoe shining on the tape if an incremental to disk gets upgraded to a full to tape. Be a thing to have. Another thing I came across, you cannot copy jobs from one storage to another if it was using a base job. That probably has a technical reason, but it's not very nice because I want to have a second copy of my cluster, whatever, 60 machines, I want to have a copy of that. And the max interval we talked about just a few slides ago. All right, if you want the configuration files we use, you can have those and just send me a mail to the address. I won't answer questions now, but hold those off for after my colleague finishes, which I very fondly like to.
Good morning. So, this is the second part of Bareos and Scientific Environments. Now this is another Max Planck Institute, which is Max Planck, but still very different from the other Max Planck Institute, because we are not doing radio astronomy, we're doing metabolism research these days. It used to be neurological research. We changed the name quite recently. So this is what the institute looks like. It's on the University Hospital campus in Cologne. Right, I don't think we have a lot of time for that just now. That's just a little introduction where most of our data is coming from. This is a machine for magnetic resonance imaging, similar to what many hospitals have these days. This one is a bit nicer, of course, but still the basic principle is the same. We use that machine, amongst other things, for diffusion MRI. Fiber tracking is one of the buzzwords. And fiber tracking is interesting because you want to know something about connectivity in a brain. And it takes a lot of compute power, it takes lots of storage, and it makes for some really nice images. Okay, but I don't think we should go further into this. This is another type of tomography. This is a kind of tomography you don't see very often because in order to operate this, you need a whole radiochemistry department, and that takes a lot of money, a lot of manpower. So this machine looks kind of boring from the outside. This is the machine we developed some years ago with a company which is now Siemens in Tennessee. And it's a prototype, and it used to be the most powerful positron emission tomograph in the world. And it's quite revolutionary from the inside. We also don't have time to go into that. Suffice it to say that this is where the proband's head is. Okay, so it's a positron emission tomograph, which means that we inject radioactive traces into the brain. Obviously, only very tiny amounts of radioactivity. Okay, but this is not today's topic. As you could see from the abstract, we've been using SAMFS, which is one of the better known HSM file systems. And our problem is that we have rather complex projects involving many very different kind of scientists. Not all of them very computer friendly. And those groups tend to be very heterogeneous, which is also a very polite way of saying. And good scientific practice mandates that you have a fine granular backup for obvious reasons. So we used to have this SAMFS file system from Sun, and over the years it was expanded to about 50 terabytes online space. And we have SL500 library with LTO4 drives. And when that was full, we ran into several problems. One of the problems with HSM file systems is that this happens at some stage inevitably. You don't have enough online space. If you have users using these file systems in a production manner, I'll come to that in a moment. Yes, this is also a very polite way of saying this. If you have an HSM system, you have to differentiate between online and offline data. And you can try to explain that to scientists a lot of times, and still they find it very difficult. One of the problems was that we had a very reliable, very nice photo. I really like that machine. It's just the one machine. And this is a bottleneck, naturally. Okay, and some years ago, with a lot of help from our esteemed colleagues from the Radio Astronomy, they sort of got us on the chase. We started using an ESX cluster, which is not that unusual. So that was running in parallel, and it was pretty obvious from the very beginning that this was becoming increasingly important, because within a very short time, many vital services moved to that system because it worked so smoothly. And we are running Linux wherever we can. And so very early on, the problem was that how are we going to back up virtual machines? And a long time ago, I was used to using Solstice Legato backup, which is, from my point of view, a very nice kind of product. We had Backup Backsec for some time for Windows. Unfortunately, we need to have some Windows machines. And then they made a very aggressive pitch buying our previous licenses, although they had long expired. So it was very cheap for us. but it was very unsatisfactory, and I'll come back to that in a minute. So these days, we use data core for storage virtualization. So we have storage in several server halls in several buildings, in fact, and they have independent power supplies, and that works remarkably well. But still, the problem is, how do we back up that data? So we got another idea from our colleagues in Bonn, and the concept is to use Grau Open Archive, and we got a nice tape library, which we operate together with another Max Planck Institute. So it's a partitioned library, very cost-effective. But then we found that we were a bit naive when trying to map our existing HSM concept from SAMFS to Grau Archive Manager. The problem is that these HSM systems have a different focus, and I'm not saying that SAMFS is more mature, which is maybe a little bit. The Grau system has different strength, and it's just one of these cases where you need to rethink and come up with different concepts. And it was just something which surprised us, that we had lots of HSM-type file systems, and several of them using the same tape pools. There are some cases where this doesn't make a lot of sense. In our cases, that made some sense. This is something you don't do with the Grau system. So we need to come up with a new concept. Also, it's highly advisable to reduce the number of file systems. So we tried something very different. That was a suggestion from Detlef Jan. I'm very grateful that he came up with that. He said, why shouldn't we try, and some other institutes were thinking about too, namely our colleague in Leipzig, Helmut Heid. He said, why don't we try to back up to disk, but use an HSM file system for that? And the answer is, yeah, why not? It works marvelously, at least for us. So, in fact, it works so well that we think that we will drastically reduce the amount of HSM-type file system available for scientists and use Bareos for fine granular backups. So this is one of the systems that belongs to our ESX cluster. We have a couple of those. We have about 100 virtual machines. One thing which is a bit unusual, maybe, we actually use some of these virtual machines for scientific computing. That is also a bit unusual in the sense that some of these nodes have a lot of memory. And for some projects, we need compute nodes with a lot of memory, and it's very convenient to dynamically configure them if you need them. And it's much more cost-effective than having some pizza boxes sitting around with lots of memory and nobody uses them, or somebody uses them but only for a very short time. This is what the new tape library looks like. And this is, as I mentioned before, very cost-effective because it's partitioned and we're using it for 2 institutes. We only use LTO6, write once, read many tapes. And this is why in this config we don't recycle, because that doesn't make sense. So we use a template-based approach for adding clients, and we've inherited that from Jan, thank you. And if people might think that configuring these clients is a hassle or it's complicated, it's just coming up with 2 templates, a 4-line shell script, and then this is all it takes to add another client. And I think that works beautifully. Backup to disk on HSM. This is what it looks like. And if you do a backup to disk on an HSM system, you have to take 2 or 3 things keep in mind. You should put an upper limit on the virtual tapes. That makes a lot of sense. If it's 2 GB, 5 GB, this is a matter of taste, really. 5 GB works very well for us. Okay, now this is getting more interesting. The one thing you don't want is Bareos writing to this file system. Bareos doesn't know it's an HSM system, so it's a normal file system. So the one thing you don't want is Bareos writing to a file and maybe 2 hours later adding to that file, maybe 4 hours later adding another few bytes. From the point of view of the HSM system, this means that you save that file at least 3 times, which is a waste. So there's an easy way around this. You set min file age on the HSM system to 10 minutes or something. And from our experience, there's no period of any significant length while Bareos is writing a virtual file, which will exceed that. And you configure 1 job per virtual tape. And this is what you see here. You see a maximum of 5 GB in these files, and usually quite small files, because this is a small database server. I use this as an example here. So these are small increments, and this is the bi-weekly full backup. Okay, we have a number of small database servers, and the nice thing about them from a current perspective, they're very small indeed, but they're still very important to us. So one thing that has been working very well for us over a number of years, this is what we've been doing before we started using Bareos. We have a cron job that creates dump files for each database several times a day. It's just a few megabytes each run. And we store them locally on the server. Okay, there's another cron job that runs daily and makes sure that old and very old backups will be deleted as necessary. So it still means we usually have hundreds of snapshots there if we want. Okay, and then we run Bareos several times daily. It doesn't cost anything. And so those dumps, they get timestamps. We compress them. They have a beautiful small size. And Bareos saves them. Nice concept. Another thing which works pretty neatly, I think, is we have some databases with proband data, and obviously you want some improved security on them if possible. And we used run before and run after hooks. On the ESX cluster, it's pretty easy to configure virtual network cards. And we have one extra network board in the database server and one in the Bareos server. We use sudo to grant user Bareos permission to activate virtual network board F1 and also to deactivate it. So, before each backup job, that board goes online. After each backup job, it will be deactivated. It is not perfect, but it is improved security, and the result is that only during the very small backup window, it takes 1 minute, 2 minutes maximum, there will be a physical connection between the Bareos server and the database server. That's just something we tried, and it worked from the start. No flaws whatsoever. And those are shell scripts. Those are just one-liner. It's if up F1 and if down F1. This is maybe a bit amusing. This is a mail report. This is not a Bareos mail report. This is the kind of mail report I will never ever want to see again. This is a Acronis mail report. It contains gibberish. It contains loads of gibberish. It, on the other hand, doesn't tell you how much data was copied. It doesn't tell you on which media the data was copied. And to add insult to injury, really, it will tell you on the box, yeah, we do full Unix backup. Okay, I'll stop with that now. The thing really is what we liked about Bacula and Bareos from the very beginning. Looking at the mail reports, that was almost as good, if not better, than my Legato backup reports 10 years ago. Beautiful. Everything I need to know is in there and not much more. Nice. The other thing I really love about Bareos is that one of the very first things I did is I used some independent command line tools to look into the database, and I liked what I saw. The nice thing is that really, without any documentation, it's nice to have documentation actually, but it's even nicer if you don't need it. In a perfect world, you don't need it but still have it. Which is more than you can say about 2 or 3 chapters in the current Bareos documentation. But then this is a slide about what I really like about Bareos. I really like the database. I can do things like that. Yeah. This is perfectly clear, easy to understand. This thing will just. I need to know what the name of my client is. It will give me the last 500 jobs. And everybody who has some experience with system administration probably can tell you that if you take looking at logs or looking at, in particular, incremental backups seriously, you can learn a lot about your systems and if they're healthy or not, because you can recognize patterns easily. Well, we even like the very special appeal of bconsole, but I have to add, then we also like Emacs and the other thing. So maybe we have a little bias there. This is, I think, my final slide, and this is one of the nicest things. This is my main selling point about Bareos, really, I think. This is some code. It's mostly not mine. This is something I found with, I think, that was the second entry when I Googled for something. So it wasn't particularly difficult to find. The only difficult thing here, this is why I needed to look it up, is I very quickly found that although the database is beautiful, you need, for 2 or 3 things, you need external information. One is how the checksums work, and the other is this kind of thing. Okay, this is a bit weird. But there's a ready solution for that. So if you have the solution for that, the rest is then very simple. And so we started using Bareos in seriousness, and then I looked at the files. And I have this number of Linux virtual machines. And I know for a fact that over a weekend, I don't have any users changing anything in my MySQL databases. So I wondered, okay, nobody uses them, but why is there still incremental data coming in? And I wanted to know, what are these files that get changed even on a Saturday? It's pretty easy to find out. You do an incremental backup. You use that kind of script. You can think of hundreds of variations from that. I call it largest from job ID. So you look up the job ID from your mail log or wherever you keep it, and it will tell you, okay, this is from the day before, this is okay. We do binary logging on our database. Okay, this is fair enough. This is what you expect. This is what I didn't expect, mlocate, where you can look it up, okay, and that there's a cron job on systems, even if it doesn't make sense at all, you can switch it off. But this is how I learned, okay, there's mlocate. It's not a terribly important thing. It's not a lot of data that you waste if you keep that running, even if it doesn't make sense. But it's nice to get a feeling what your machine does. It's nice to increase your understanding about how your machines work. I think that's a good last line.